in some way. With elementary calculus knowledge, the following equation can be proved true. In other words, the derivative of the volume of a sphere is equal to its surface area. Is this a mere coincidence, or can we derive this relationship mathematically? First, we must derive the volume of a sphere.
We consider the equation of a semicircle of a radius r to be y equals the square root of r squared minus x squared. To convert this equation to a sphere, we rotate about the x-axis. As a sphere is made out of many small cylinders, we can integrate the equation of a cylinder with height dx to find the volume. We then substitute the radius for y, substitute the equation for a semicircle, and integrate from negative r to positive r to find that the volume of a sphere is equal to 4 over 3 pi r cubed.
Next, we're going to talk about the derivation of the formula for the total surface area of the sphere by integration. So, as we know that we have the equation of the semicircle of radius r, and we have converted this into a sphere, and we have rotated about the axis. So we have the figures 2. So if we consider the surface area of this strip from figures 2, which is the red part, we have the equation ds, where dl is the differential arc length. We can obtain dy dx by doing the derivative of y. So the total surface area of the sphere will be the sum of the differential area from minus r to r, which is equivalent to the twice the sum of the differential area from 0 to r. So we have the equation SA, and then after doing all the integration, we will end up with SA equals to 4 pi r squared, and that's our equation for the total surface area of the sphere.
I'll now be discussing the connection between the surface area and volume of a sphere. We first start with the volume equation already established as 4 over 3 pi r cubed. And so we can view this as a total sum of surface area as spherical layers with extremely small thicknesses stacked inside one another. And we can see the diagram below that shows this. So we get the surface area in respect to r, which is the radius of each spherical layer, and we then multiply this by the thickness of each layer given through L. And so using the total volume equation, the limit as spherical thickness L approaches 0, the equation then becomes the surface area in respect to r dr. And so we substitute the total volume equation for the volume equation. And so we make both of these equivalent to one another and then differentiate both sides with respect to the radius dr. And so we can then see that after this differentiation, the derivative of volume with respect to r is its surface area, which is 4 pi r squared.
In 2 dimensions, if we uniformly distribute points within a square and note what points fall within its embedded circle, as the total number of points n goes to infinity, the number of points inside the circle, n inside, divided by total points n, is equivalent to the area of the circle divided by the area of the square. Thus, using this equation, we can approximate the area of a circle. This idea can be extended to 3 dimensions.
We can approximate the volume of a d-dimensional sphere of radius r using the following Python code. For approximating surface area, we can employ a similar algorithm. Instead of points, we uniformly distribute small line segments of length L and note how many intersect with the surface of a sphere.
Using both Monte Carlo methods, we can test the validity of the volume surface area primitive derivative connection for single cases in higher dimensions. If, for example, we can accept that the volume and surface area of a 4-dimensional sphere is this, then for r equals 1, we get the following calculations. Then running Monte Carlo simulations using the algorithm in figure 5 and equations 3 and 4, we can find experimental solutions for the following test conditions in order to find the volume and surface area of a 4-dimensional sphere. While it is not a proof of equations 5 and 6, our experimental solutions closely approximate the theoretical solutions for r equals 1, increasing the likelihood that equations 5 and 6 could be true formulas for a 4-dimensional sphere. If our algorithms are correct, then our experimental results should be consistent with theoretical formulas for any dimension and for spheres of any radius. In our report, we have derived formulas for the volume and surface area of a sphere, as well as proved the primitive derivative connection between them. While we have not proved this connection true for high dimensions, we have derived algorithms to approximate volume and surface area for spheres of any dimension, which justify the primitive derivative connection for specific cases.
letting her know when we're leaving somewhere. And she just happens to be going in.
Thank
Okay, thanks. So I know you have 5 people